This conference will now be recorded.
Hello everyone, the topics that we are going to discuss today: intermolecular forces versus thermal energy, and then there will be gaseous state, physical characteristic of gases, and different laws for gases. Probably we'll be able to finish only the first law, which is Boyle's law. Fine. So intermolecular forces, we have already seen what it is, and there is another term, thermal energy, which is obviously related to temperature. Now these two, basically depending on the balance of these two opposing forces, the matter it will remain in which state, that will be decided. Okay, so if intermolecular forces are very high, that means the molecules, atoms, they are very close to each other. In that case, you can expect it will be in more denser form, that is solid state we can expect. But if thermal energy is predominating over intermolecular forces, now the distance between atoms and molecules, it is very far from each other. So now there is a chance that it will remain in gaseous phase. So depending on which one is dominating over each other, depending on that we can have different types of states. So thermal energy is energy of a body which is because of the motion of its atoms and molecules. So all the atoms and molecules, they are never in static condition, they are always vibrating. That is, the bonds are always vibrating. Fine. So that is why there is thermal energy associated with it, because of this type of motion. And from this thermal energy, it is also the measure of average kinetic energy of the particles of matter. So if it is very high, that is thermal energy, if it is very high, then kinetic energy of the particles of the matter, that will also be very high. And thermal energy, remember, as the term suggests, thermal, that means it will be directly proportional to the temperature of the substance. So when we increase the temperature, thermal energy accordingly will increase. It is responsible for the movement of particles, and that is why it is known as thermal motion. So the motion that is generated because of the movement of particles, that is thermal energy basically. This type of motion is known as thermal motion. So as you can see in this picture, when you are increasing thermal energy, that means heat up, then there is a chance we will move from solid state to liquid state and finally gaseous state. Because when it is solid state, the distance between the particles, it is almost nil. They are very close to each other, tightly packed, right? But when it is liquid, now comparatively, that is compared to solid state, there is large distance between the particles. And when you are switching to gaseous state, now the distance is very, very large. So you can see within a fixed volume, because this square, if you consider it is a fixed volume, now from solid to liquid to gas, when we are moving, the number of particles are decreasing. But if you are increasing intermolecular forces, now gas will be converted to liquid and liquid will be converted to solid. So it is opposite. You are increasing thermal energy, so it will move from solid to liquid to gas, and when it is the reverse process, that is the opposing force, which is intermolecular force, when it will increase, that means the interaction between the particles will increase, and as a result they will come to each other, the distance will decrease. Fine. Intermolecular force of attraction, they helps to keep the particles together, obviously, because when it is very high they are close to each other, but thermal energy make them move apart. So opposite roles they are playing. When thermal energy of molecules is reduced by lowering the temperature, then only you can liquefy the gases easily. So when you want to move from gaseous state to liquid state, obviously what we have to do, this distance, large distance between the particles, that we have to decrease. Then only you can liquefy it easily. So thermal energy should be minimized. And how you can do so? If you lower the temperature, then thermal energy will be minimized and the particles can come close to each other. And as a result, now we can convert them from gaseous state to liquid state. So here we have another picture. Solid, when it is we are increasing temperature, the process is known as melting and it is converted to liquid. Similarly, when it is vaporization process, or you can call it boiling, now it is converted to gaseous. And when we are moving in the reverse direction, that means from gaseous state when we are moving to liquid state, now the process is known as condensation. Okay, just follow the blue arrow. And when you are moving from liquid to solid, now the process is solidification, or the associated temperature we call it freezing point. So at freezing point, solid to liquid or liquid to solid, but depending on what you are increasing, whether you are increasing the temperature or decreasing the temperature, depending on that, solid will be converted to liquid or vice versa. So remember these processes: solid to liquid melting, then liquid to gas vaporization, that is conversion from liquid state to gaseous state, and condensation process means gaseous state is converted to liquid state, and solidification or freezing, it means liquid is converted to solid. And from this direction you can understand thermal energy lost when you are moving from right hand side to left hand side. That means if you follow the blue arrow direction, then thermal energy is lost. So that is the reason they can come close to each other and we can move from gas to liquid to solid. But if you follow this red arrow, now thermal energy is gaining. So that is why solid to liquid, then liquid to gas we can convert. So the existence of different states of matter, it is nothing but a balance between its intermolecular forces. Though this line we have seen it before. The existence of different states of matter, it is nothing but a balance between these two opposing forces. Intermolecular forces and thermal interaction or thermal energy. How much thermal energy present between the particles, depending on that, you will have different states of matter. Okay. Now we will focus on gaseous state, because in this chapter, that is states of matter, in this chapter, it is mainly the gaseous state that we have to consider. So gaseous state, what are that is different statements you will be seeing here that is related to gaseous state. So atmosphere, that is the atmosphere in which we live, that is actually a mixture of different gases. That is, naturally all these gases are present in the atmosphere, and we know oxygen and nitrogen, that is 78% almost, and then oxygen, CO2, ozone, water vapor, that is water, it remains in vapor form. So it is mixture of different types of gases. It is not limited to only these 5, there are many other, but these are the important ones. Now the gaseous state, it is the simplest of all the states. That is, if you consider solid, liquid and gas, obviously this is the simplest state. And in the whole periodic table, that is out of all the elements, only 11 elements are present. Under normal condition, they are present as gaseous state. Okay, so under normal condition, when I am saying, I mean to say it is actually the standard temperature and pressure, and which is known as STP condition, standard temperature pressure, STP, which is 1 atmospheric pressure, and in Kelvin scale the temperature is 273. So when this condition is present, then all the elements, if you consider in the periodic table, only 11 elements are present in gaseous form under normal condition, or you can say ST. So these are the 11 elements, as you can see here. So here the whole periodic table is not shown, only you can see we have hydrogen, that is from group number is mentioned, then from group 15, 16, 17, 18. So all these are basically P block. So from P block, these 4 groups, if you consider, we have nitrogen, oxygen, fluorine, chlorine. So among halogens, we know there is FCl, Bri, but only fluorine and chlorine, they remain in gaseous form under normal condition, not bromine and iodine. Iodine is solid, bromine is liquid. And all the noble gases that you can see here, all are basically gas, because they are in monoatomic gas. Fine. Among these three states, the gaseous state can be observed to have the largest intermolecular distance. So this fact we already know. So out of that is, if you just compare these three states, only in gaseous states, the particles, that is the intermolecular distance between two particles, that is actually very high compared to the other two states. Now one question may arise in your mind that sometimes I am using the word gas and sometimes I am using the word vapor. But don't think these two are same. Obviously, there is difference between these two terms. So when I am saying gaseous state or gas, that means under normal condition, that is under STP condition, 180 M to 73 Kelvin, the elements are present as gas. Okay. So here it is also mentioned room temperature, which is nothing but this 25 degrees centigrade, and 1 atmosphere pressure. Fine. So while vapor, that is, this is all about gas, but if you consider vapor, then vapor is the gaseous form of any substance, but not necessary that vapor, it has to be under normal condition. So it is gaseous form of any substance. It may be gaseous form of some liquid, it may be gaseous form of some solid, and that is also at room temperature and 1 atmosphere pressure. So as example, I can say, as you can see all the elements here, that is nitrogen, all these gases that are mentioned, that consider these gases, that is, I'm not talking about compound, only one element. So here nitrogen, oxygen, under normal condition, they are actually in gaseous state. They under normal condition, nitrogen is not liquid or solid, oxygen is not liquid or solid, right? So when you will use this, that is, you cannot say that nitrogen vapor or oxygen vapor. So you should use the term gaseous for oxygen or nitrogen. Fine. But suppose I am saying water. Now whether I should call it gas or I should call it vapor, which one is correct? Now in this case, you cannot use the word gas, because when it is water, under normal condition, it is not present in the form of gas. It is present as liquid under normal condition. So when you are increasing the temperature to 100 degrees centigrade, which is the boiling point, then only it will be converted to gaseous form. So that is, it is not present as gaseous form under normal condition. Only when we increase the temperature, then only it is converted to gaseous form, that is after reaching boiling point. So for water, you should use the term vapor, not gas. So that is the difference between gaseous, that is gas, and vapor. So gas is a substance that is normally in gaseous state, but if when you are using the term vapor, be careful that it is actually the gaseous form of any substance that are under normal condition, not in gaseous state. So for example, here F and Cl, these two halogens, they are under normal condition. Yes, but suppose if I am saying bromine or I am saying iodine, that is diatomic bromine. Now under normal condition, bromine is yellow colored, that is very deep yellow colored liquid, and iodine is violet colored solid. Okay. So when I will consider their gaseous form, you should say that it is bromine vapor or iodine vapor. It is not bromine gas or iodine gas. Fine. So in this way, we have to differentiate between gas and vapor. Fine. Physical characteristic of gases, some more properties we'll see for gases. The intermolecular forces between these gases are negligible. That we already know, because that is the reason why the particles can remain far from each other. Because if intermolecular forces are very strong, obviously the distance will be very less and it will not be present in gaseous state. So intermolecular forces are not significant, they are negligible. That is the reason they can move freely from each other, that is the particles of gases. Then the next statement, they exert equal amount of pressure in all directions. So suppose we have many gaseous particles, they can exert pressure, equal pressure in all the directions. Fine. These particles move at high speed in all directions, and as a result they can hit each other. So as they are freely moving, so suppose it is freely moving, so it can hit it, or it can hit it like this, or if there is another one, any direction it can move and it can hit each other. So as a result, what is happening, because of this random hitting, it causing the gas to spread evenly throughout the container they are kept. So suppose you have a container, sealed container where some gas is present. Now in a particular room, if you are placing this container at a corner and then you are opening the lid, now what will happen? The gas, it will spread all over the room. Okay, so it will spread evenly throughout the container, and the reason is that they can move at high speed in all the directions and they can hit each other. And because of this property, and that is possible because intermolecular forces are very negligible. So immediately they will spread evenly throughout the space available. So this also causes them to exert pressure on the walls of the container. So suppose in any particular container when they are present, as they are randomly hitting each other, so obviously when they will be close to the wall, they will also hit the wall. So that is the reason they can exert pressure on the walls of the container. The volume and shape of the gases are not fixed. They can take the volume and shape of the container. So that is expected, fine, because depending on how much space is available, how much volume is available, what shape is available, depending on that, because whatever space is available, they will always spread evenly. That is the property. So this is important difference if you compare with solid and liquid, because in case of solid, obviously volume fixed, shape is also fixed, so we cannot expect it. And in case of liquid, if you consider, in case of liquid, volume is fixed but shape is not fixed. So that is why you can depending on, you are putting water in glass or you are putting it in some bowl, it will take its shape, but volume is fixed when you are considering liquid. But when it is gas, neither volume nor shape, nothing is fixed. Okay, so this is important difference between solid, liquid, gas. And this is the reason gases, they can mix evenly and completely in all proportions without any mechanical aid. So suppose we have gas number 1, then we have gas number 2. In this way, if you mix all these, they will evenly mix with each other and you do not need any mechanical aid. Suppose when we are mixing one liquid 1 and we are mixing another liquid 2, then we sometimes we have to use some mechanical starter, because the particles of these two individual liquids, they cannot move so freely like gaseous, because compared to gaseous, in this case of liquid particles, now the intermolecular forces are comparatively high. So that is the reason they cannot move so freely. Obviously compared to solid it is free, but not so free like gaseous. So that is the reason sometimes you may need some mechanical aid, external help is required. But when it is gaseous, even without any mechanical aid, any gas when we are mixing, that is, the particles will mix each other. Fine. Now these are the properties of gases. Next you will see different gas laws. Okay, and these different gas laws, one by one we will see, but some common points for before starting the discussion of different laws for gas, we have to see these statements. While a real gas has negligible intermolecular force of attraction. So this point we have mentioned in the previous box. You can see that intermolecular forces are negligible. But this is for real gases. That is the gases we see in our everyday life. Okay. But if you consider the ideal nature of gas, though in bracket it is mentioned no natural existence, ideal gas, they do not exist. Fine. So it is ideal situation. So suppose if there is any existence of ideal gas, there will be zero intermolecular forces of interaction. But when it is real gas, actually not when, all the gases are real, Ideal case is imaginary, but ideally there should not be any intermolecular forces. But actually there is negligible amount of intermolecular forces. Fine. Now details of this difference between ideal gas, real gas, there is a specific, there is discussion that we will do later after finishing these laws. Okay, so this statement that is mentioned here, real gas, how their behavior is different from ideal gas, how they are deviating from ideal gas, all this will be discussed later. Right now just remember that real gases, it is not that intermolecular force of attraction is zero, it is negligible. But if it is ideal condition, it is zero. Real gases behave most ideally when it is high temperature and low pressure condition. So pressure is high, temperature is low. If you can somehow maintain this condition, then it can behave nearly to ideal gas. I am not saying it will be exactly ideal gas, but this is the condition where you can expect them to behave ideal. Fine. Their behavior is governed by some general laws, and all these laws are discovered as a result of experimental studies. So you will never see some common laws for solid or common laws for liquids, but when it is gaseous state of matter, there are some common laws, that is the laws that are applicable for any gases. This is unlikely in case of solid and liquid, because some properties of gases are present that are common for all, and that is why you can have some general laws which you can apply for different gases. Suppose you can apply for water vapor, then oxygen, nitrogen, CO2. But these type of laws you will not see for solid or liquid. Now these laws, one thing you will see that is common, that is pressure, temperature, volume, and sometimes there is number of moles also. So pressure, temperature, volume, based on these measurable properties of gases, these laws are based. That is, these laws are basically some relationship. What kind of relationship? As you can see, I have here written PTV, pressure, temperature, volume. So suppose you want to have some law which is based on P and T. So you as gaseous, that is these properties, they matter. So when you are comparing the relationship between P and T, that is pressure and temperature, how they are changing with each other, obviously you have to fix volume. Because if you are not fixing volume, you will not be able to understand that when you are changing P, what is the effect on T or vice versa. Similarly, if you want to see the relationship between P and V, you have to fix T. So in this way, you will see that in some laws, it is relationship between TV, then PV or TV like this. And there is combination of all these laws together. There is ideal gas law, which is PV equal to NRT. But first, one by one, we will see the relationship between P and V, then V and T, and P and T. Okay. So the first law is pressure volume relationship. So obviously you can understand now temperature will be fixed. Then only you can compare P and V. So Robert Boyle performed a series of experiments to study the relationship between pressure and volume of gases. Fine. So this is pressure volume relationship. Now what is this law? It led him, that is the experimental results, led him to conclude that at a given temperature means temperature is fixed. You have to do it, okay? Otherwise, how you will understand the relationship between P and V? Under this condition, the volume occupied by a fixed mass of gas. Now see another quantity we have fixed, which is mass. Now you can also say that when I am saying fixed mass, obviously the number of moles fixed. So mass fixed, temperature fixed, then only you can have the relationship between P and V. And what is this relationship? Under given condition, volume occupied by a fixed mass of a gas is inversely proportional to its pressure. Inversely proportional means when you are increasing pressure, volume will decrease, and vice versa. This law is applicable to all gases, regardless of their chemical identity. Okay, provided the pressure is low. So as I have said that when pressure, you can see, it is low pressure and high temperature. I have written it wrong. Temperature high, pressure low. Okay, so then only you can apply these laws. So this law, as I have said, these laws are basically general laws. You can apply for any gases, which is unlikely in case of solid or liquid. So that point is mentioned here. You can apply it for any gases. Now we will see the mathematical terms, but before that, look at this pictorial representation. So this is the volume occupied by the gas. Okay. Now we are increasing the pressure by this piston. So when pressure is increased, suppose here pressure is P1, volume is V1. In the second case, now it is P2 and P2 is greater than P1. And volume is, that is second state, the volume is now V2. So it is less. So V2 is lesser than V1. Okay. So in this way, it is inversely proportional to pressure. Now the mathematical terms. P is inversely proportional to V, so that is why it is, you have to write in this way, 1 by V. Now if you want to remove this proportionality sign, then you have to place K. You can also write it like this, P equal to K by V, and then finally P into V, just bring V in the left hand side, PV equal to K. So this K is constant, which is known as proportionality constant. And as it is constant, that means for the initial state when it is P1 V1, then also it is equal to K. For the final state P2 V2, then also it is K. So you can put any subscript here depending on in which state it is present. So P1 V1, P2 V2, in this way if you are increasing the pressure further, another volume you are getting P3 V3, or it may be that you are decreasing the pressure, that is you are moving the piston is opposite direction. So suppose this is P4, then obviously as pressure is low, volume will increase. Okay, so the direction will be towards this. So whatever it is, the multiplication of these two terms under same state, I mean, it will always be equal to the value K. So that is why P1 V1 equal to P2 V2. What you can write? P1 by P2, V2 by V1. So different relationship you can derive, but the important thing that you have to keep in mind is this first one. Once you know this, you can make different mathematical expressions. So just remember this. After all, everything you can do on your own, but first relationship is important. If we consider graphical representation, so we have taken V in x-axis and P in y-axis. Fine. So when it is inverse relationship, it is not just for P and V. Suppose in general, if I write some quantity X, it is inversely related to Y. Then also same type of nature of graph you will get. And how you are getting this type of graph? Suppose this is P1. And as we know, in the previous, I have written it, P2 is written. So suppose P2 is somewhere here. So when it is V1, V1 is greater. That means V1, if it is here, V2 will be here. Now if you join the line P1 and V1, so it is somewhere here. And when you are joining the line P2 and V2, that is, this is the value for V2 and this is the value for P2. If you increase the line, it will cut it here. So in this way, if you take different values of P and V, P2 V2, P3 V3, P4 V4, all the points that you are getting, when you will join it, you will get this type of curve. It is true for any two quantities that are inversely related to each other. Not necessarily it has to be P and V. It is just mathematics. That's it. Fine. So as it is inverse relationship, when the value of P is very high, suppose if you just consider any point somewhere here, So this is a very high pressure, right? Now if you draw a line over the x-axis, the volume at V, that is the volume at x-axis where the line is cutting, see, this is very close to 0. Similarly, in x-axis, suppose you are choosing any point which is very high. Suppose this is V, any value of V which is very high. Now, under this condition, if you increase it, it will cut it here, and if you extend this line, it will cut the y-axis here. That means now when V is very high, pressure is very low. So I hope now you can understand how this type of nature of graph you are getting from P inversely related to 1 by V. So it is simple. You have taken P in y-axis, V in x. But suppose if you have taken P in y-axis, which is just like before, but instead of taking V, now you have taken 1 by V. And the nature of graph is completely changed, right? Why it is so? Now look at these terms. That is the first term I am talking about. P is proportional to 1 by V. So when P is proportional to 1 by V, you can easily write P equal to kV. So it is like this. P equal to K some constant into 1 by V. So you can compare this equation with Y equal to M into X. So here 1 by V, it is comparable to X. K is the slope and this is the quantity for Y. So when you are considering 1 by V, not V, then it is proportional to P, and any directly proportional graph, it looks like this, right? So try to understand difference. It is very simple. Don't think it is something complicated. When you are considering V, it is inversely proportional. So in terms of V, you are comparing how it is changing with P. But if I am saying what is the relationship between P and 1 by V, I'm not saying V. So in this case, P is directly proportional to the quantity, that is a whole quantity. Now if you consider, it is directly proportional. So that is why when you are taking the value 1 by V, the nature of graph is like this. So in this case, see, suppose you are choosing any small volume close to 0, suppose here, just extend the line. It is cutting it here, and if you extend the line, this is the corresponding pressure. Choose another point in V which is compared to the previous value high. If you extend it, it will cut it here. Now this is the corresponding pressure. So see, when V you are increasing from this value to this, P is also increased to this to this. So in this way, the nature of graph is completely changed. Fine. So graphical representation you should know, because based on graphical representations, questions you may get. This PV relationship, we can understand it as the pressure is because of the force of the gas particles on the walls of container. So we have just said so many things about pressure, and the pressure is generated because of this force of these gas particles on the walls in the container while it is kept. If a given amount of gas is compressed to half of its volume, now obviously the density is doubled. Density means what? Mass divided by volume. Mass is fixed, but suppose this is D1 and this is volume 1. So volume from 1, keeping the mass fixed. Now when you are, now the volume is half. That means you have, suppose, volume 2. Volume 2 is lesser than volume 1, and this new density is 2. So mass is fixed. So if you take the ratio of these two, so it will be volume 2, mass will be cancelled by volume 1. That means yes, D1 by D2. So as volume 2 is half of volume 1, so obviously density, that will be D2 will be equal to 2D1, because volume 2 is half compared to volume 1. So this new density, it is 2 times of the old density. So density is now doubled as the number of particles. So this is the mathematical way by which you can understand, but theoretically how you will understand? When you have suppressed the volume, that is better I use the term compressed, not suppressed. Compress the volume to half of original amount, original value. Now the density is doubled, and the reason is, this is a mathematical explanation, but what is the actual reason? The number of particles hitting the unit area of the container, that is actually doubled because volume is compressed. Hence, pressure is increasing twofold. So this is the explanation. We have already seen that P is inversely related to V. But when volume is half, that is new volume V2, that is half of V1. So in this case, obviously, the new volume, new pressure P2, that will be double of the previous value. So pressure would increase twofold. Okay, so this is a theoretical explanation. You can consider the pressure density relationship also you can get from Boyle's law. So here you have already seen that mass by volume, that is density, and from Boyle's law we can get different relationship between PV, that is you can express it as PV equal to K or P equal to K by V, or you can say P1 V1 equal to P2 V2. In different ways you can consider the equation for Boyle's law. But here we will see how pressure and density, the relationship between P and D from Boyle's law, how to get it, that we will see there. So from Boyle's law you already know this, right? Now in place of V1 we can write mass by density. So see, the same equation you can write, instead of writing V1, now we have written m by d1. So m is basically mass. So we know that mass by volume, that is equal to density. So when it is volume, that must be mass by d. So in this case it is small d, but if you put the subscript, it will be m by d1 for v1, m by d2 for v2, and m is fixed. So instead of writing v1, you have now written m by d2 and m by d1. Left hand side, right hand side. M will be cancelled both sides. So now what you are getting? P1 by D1, P2 by D2. Or you can write P1 D2 or P2 D. But important point is what? Important point is pressure and density. These two are directly proportional. So here M is mass, D1, D2 are the densities of gaseous at the pressure P1, P2 respectively. And in this case, density of gas is directly proportional to pressure. So see, look at the subscript. When you have multiplied this, it is 1, 2, 2, 1. Now see here, it is 1, 1, 2, 2. So 1, 1, 2, 2, same subscript you will get when you are multiplying. Only when these two quantities are inversely related. But when you are getting this type of subscript, 1 and 2, 2 and 1, then obviously it means it is directly proportional. So pressure is or density is directly proportional to pressure. This you can see. So when you are increasing pressure, density is also increased. And that is also mentioned in the previous explanation that when pressure would increase twofold, density is basically also twofold. Fine. Now this relationship will be important when you will solve any problem. Suppose P and V given, that is the values are given or mass given, and you have to find density, or it may be that density is given, other quantities are not known, you have to find that. Okay, so to solve problem we need to know how density and pressure, these two are related to each other. So two graphical representation we have already seen, but that is not enough, we have to know some more graphical representation for Boyle's law. Here we have taken PV in y axis and x in p axis. Now this line that you are getting, it is parallel to P. That means whatever is the volume of P, suppose this is P1, this is P2, P3, whatever is the volume, if you draw a line which is cutting here, and all these lines, their corresponding value in the X is this one. That means this product P and V, it is fixed, whatever is the value of P. Now it has to be like that, because we know from Boyle's law that PV is equal to K. Now this quantity, when you have multiplied P and V, it is always constant, whatever is the value of P or V. So that is why PV is not changing, because when you are changing P, basically V is also changed. So overall this multiplication value of pressure and volume, it will always remain same. So this is the nature of graph PV versus P. Okay. Next we have log P log V. How we are getting it? So we are getting it here. We know PV is equal to K. If you take log both sides, when there is multiplication between two quantities, it will be log P plus log V, right hand side log K. Now keep log P in the left and bring this log V in the right hand side. Now you can compare this equation with y equal to C plus mx. So here log V is x, which you can see here. Y is log P, which is in y-axis. This is intercept C, and here -1 is the slope. So as you can see from the nature of this graph, it is negative slope. And if you extend this line, that is just extend it, it is cutting here. So this value is basically intercept, where the line is cutting the y-axis, that is intercept or log K. So why you should know it? Because suppose in this y-axis, if you are getting any problem where values are mentioned in the y-axis and it is asked what is the value of log K. So if the value at this point is given from 0, so this is actually the value of intercept, right? That is log K. And here nature of the graph is such, it is clear that the slope is negative. Fine. So in this way you can draw log P versus log V. Next we have log P versus log 1 by V. So what we have done here, what you will do, instead of writing PV equal to K, just write K into 1 by V. That also correct. Another way of writing it. Now take log both sides. Now K is multiplied by 1 by V. So it will be log K plus log 1 by V. Now you have to compare this with the equation C plus mx. So here x is 1 by V. Yes, m is plus 1. C is log K. So this is the value of intercept log K. And log P is y. So in this case, slope is positive, which is clear. And when you are increasing the value of log 1 by V in the right hand side, log P will also increase, which is also clear here. See, this type of nature, that is positive slope. That means when V 1 by V value is high, or you can say log 1 by V is high, then accordingly log P is also increasing. And this is y equal to C plus mx type of graph. Now we will see some PV curve, but at different temperature. Until now, all the pictures that you have seen, graphs that you have seen, it is only one line, only at a particular temperature. But suppose we have this PV curve, or here you can also consider 1 by D, because P is inversely proportional to V, but P is directly proportional to D. Okay, so when you are considering P versus V graph, Basically, you are considering P versus 1 by T. Both will be having same nature. Okay. So when it is T3, that is very high temperature. Basically, whether it is T3, T2 or T1, whatever is the temperature, nature of the graph, which is same, and that has to be, because P is inversely related to V. But the lines are gradually increasing. So when you are having maximum temperature, T3, among these three, T3 is maximum. This line is high. So this is lowest. Then you are moving from T1 to T2. The line is also just in the, not below it, it is above it. And then T3 is just above to T2. So this type of graphs, lines in the same graph, they are basically known as isotherm. Isotherm means under constant temperature. Instead of taking V, now if you take 1 by V, remember P versus 1 by V, that graph we have already seen. This type of graph, remember 2 slides before we have seen it. So when you have taken the reverse, D is also reverse. So now instead of writing 1 by D, you have simply D. And here the temperatures T3, T2, T1. And you can see T3 is maximum. So this is the nature of graph. So this type of graphs, they are very important for any resolving problems, because questions related to these are very common. So P versus 1 by V curve, it is you can compare it, and when it is only V you have taken, then the nature is like this. But when there are 2 to 3 temperatures, it will be similar, and that is nature is same, but the position of this line is changing. Here also it is like this. Okay. So each line of this graph is called isotherm. The meaning of isotherm means temperature constant. So as I have said, problems are there related to this type of graph. So graphs between pressure and volume are plotted at different temperatures. So in all these graphs, 1, 2, 3, basically in 1, 2, 3, three different temperatures are there, and here T2 is high. Don't be, that is, just be very careful. In the previous examples you have seen T3 is max, here T1 is max, then T2, then T3. So graphs between pressure volume are plotted at different temperature. Which of the following isotherm represent Boyle's law? And this is Boyle's law, PV equal to constant, that we know. So this is mentioned that the gas is following Boyle's law, and another condition for temperature is this one. Now if you look at the statement 1 is A is saying that only the second graph is correct representation of Boyle's law. So let's check whether it is correct or not. So when, remember in the previous case, when it is P versus V and T3 is max, this line is above the other two. So now T1 should be above T2, T3, and that is also here. T1 because it is max, then T2, then T3. So we can say this is actually correct. So A is fine, but we will also see the other statement, because in statements it is mentioned all are correct. So we also have to check that. Individually we have to check all are correct or not. Second statement is saying that only 4 is correct representation. Now when it is log P versus log V, remember what we know? P is that is log P plus log V. Remember this relationship, log K. So when you bring log V in this side, there is a negative sign. So slope is negative. So this is also basically correct representation. We have already done it. I am not going into detail. Log P, log V, I have already explained it. You can check at that whatever I have said. And then we have the statement all are correct. And the last statement, none of these are correct. But we have already seen that 2 is correct, 4 is correct. So this is obviously not correct. And 2 and 4, see, once you know that this is correct, 4 is correct, this is not possible. So obviously one option is left, which is all are correct, because you cannot choose option A, because you know that 4 is also correct, but here it is saying 2 is only correct. So you cannot choose this option. Then a statement B is saying only 4 correct, but you already know 2 and 4 both are correct. You cannot choose it. Last statement obviously not. So which option is left? C. So even without checking 1 and 3, you can choose the correct option. But we will also see it here. Remember PV versus P, it is always parallel to the axis P. Though here we have 3 different temperatures, so that is why T1 is at above T2 and T3, but this is correct. And P when it is 1 by V, not V. When it is V, the nature is like this. But when it is directly, you have taken 1 by V, not V, then this type of nature. That is also correct. So here option C, that is actually the correct option. A spherical balloon of radius 3 cm containing helium gas. It has a pressure of 48 multiplied by 10 to the power minus 3 bar. Bar is the unit. Not necessarily it has to be always ATM, it may be bar also. At the same temperature, there is not just temperature, at same temperature and pressure, there is another spherical balloon. Now radius is different, 12. So previously 3 centimeter, now it is 12. So obviously, if it is V1, if it is V2, when radius is different, obviously volume will also be different. And V2 is greater than V1 because you can see radius is very high. Containing the same amount of gas, that means mass is also fixed. So mass fixed, temperature fixed, pressure fixed, only volume is different. So you can apply Boyle's law. So at same temperature pressure, another balloon having different radius 12 centimeter but same amount of gas will be having what pressure at the same temperature. Sorry, pressure is not fixed. Just correct the whatever I have said. It is Boyle's law. So basically mass is fixed, temperature is fixed because we are comparing the relationship between P and P. So obviously P will be different. So V1 is for the 3 centimeter balloon, V2 is for the 12 centimeter balloon. So previous temperature is 48 into 10 to the power minus 3 and final volume is high compared to previous. That means final pressure will be less. That is, and we have to apply the formula P1 V1 equal to P2 V2. At constant temperature and number of moles, which is same thing, whether you say same amount of gas or number of moles, same thing. So this is a relationship we have to use here. P1 is given in the question. V1 you have to find using the formula 4 by 3. It is a formula for any sphere. That is formula for volume for sphere. 4 by 3 pi r cube. So in our case r is 3. So we have taken it. Final volume is again the same formula, but now R is 12. So here P2 is unknown. So in this equation, you know P1, you know V1, you know V2, you only do not know P2. So very simple. P2 is equal to P1 V1 by V2. So we have written here the value of P1 because see here don't do all the detailed calculation of 4 by 3 pi 3 r cube because this 4 by 3 pi, this quantity it will be cancelled, numerator and denominator v1 v2. So don't do this full calculation, you just have to write 3 to the power 3 and 12 to the power 3. Final value is 7.5 10 to the power minus 4, but look at this, it is fill in the gap then 10 to the power minus 6. So you have to change this to minus 6 and for that you have to shift this decimal 2 digits towards right. It will be 750. So be very careful about this power of 10. What it is saying, just maintain that. So if you are getting this final value, you have to change it to minus 6, and when you are changing it, 7.5 is now converted to 750. So this should be the answer. Okay. So another law, new law, but I will not start it today because we will not be able to finish. So we are ending here. Thank you for listening.